All right, guys. Hey, in this video, we are going to be reviewing Coulomb's law and kind of how it shows up on the AP exam using, previously released test questions, both multiple choice and a couple of free response questions. And it's really, you're not always having to refer to Coulomb's law. A lot of times you will. So you want to know how to explain, why things are the way they are based on Coulomb's law. But just understanding Coulomb's law can help you come to different conclusions. So just fully understanding what Coulomb's law is telling you, can help explain all the periodic trends. In chemistry one, you might just need to know that atomic radius increases going down the periodic table and decreases going across from left to right across the periodic table. But in AP chemistry, they're not going to just ask you to rank things in order of, biggest to smallest using that trend. A lot of times you'll have to. So on the AP exam, you're going to have to, explain why radius gets bigger going down using Coulomb's law, or explain why it gets smaller going across from left to right using Coulomb's law. And you'd have to do the same thing with ionization energy and electronegativity and all that good stuff. You're also going to be using it to explain, why this dipole-dipole interaction might be stronger than that dipole-dipole interaction, or why that's a hydrogen bond, but that's just a dipole-dipole interaction. It really just comes down to Coulomb's law and understanding, what causes opposite charges to we know opposite charges attract each other and like charges repel, but what are the things that cause that strength of attraction to increase or that strength of attraction to decrease? And every time I'm going to be saying Coulombic attraction or the strength of attraction increases, if it's like charges interacting with each other, then it's the strength of the repulsion. But again, just this is a good, this video is a good lesson on Coulomb's law, but then really, how knowing Coulomb's law can help you, with different AP chemistry questions. Now, the first thing I'll say is this is the first year that they've actually had this on your formula sheet. Coulomb's law, which is right here, and it's an equation, but it just says proportional to. So it doesn't say equal. So I don't think you're going to be using this to actually calculate a value of the force of Coulombic attraction. It's just there to remind you the relationship. And so the force of how attracted things are or how strongly they repel each other is proportional to the product of the two charges. So charge one, charge two, you multiply them, and it's the absolute value divided by r squared. Now, a lot of times people say this is the radius between the two charges. Notice on your AP chemistry formula it says the separation. So it's really the distance between the opposite charges. So the closer they can get, right, the smaller this number is, the distance between them. So the less separation there is, so it would be a smaller number. That, because it's the denominator, that's going to increase the Coulombic attraction. And the overall charge, so plus one and minus one will be attracted to each other, but plus two and minus two will be even more attracted to each other. So the higher the overall charge, the higher the negative charge, the higher the positive charge, the stronger the interaction is going to be. So if it's opposite charges, they're going to attract each other more. But if it's like charges, then they'll repel each other more, the higher the overall charges. So when you're making an argument why this interaction is stronger than that interaction, it's really going to come down to why is this positive more attracted to that negative, or why is this negative more attracted than that positive, than this negative to that positive, something like that. And it just comes down to those two things, right? The higher the charge, the stronger the interaction is going to be, and the closer they can get. So the smaller the particle, the closer they can get to each other, the stronger the interaction. Okay? So radius matters. So it could be an ion's radius or an atom's radius or like the size of a molecule. The smaller things are, the closer they can get, and the closer they can get, the stronger the interaction. Okay? And so that's really how you're gonna, and because this is now on your formula sheet, I bet there's going to be maybe a few more questions on the free response where you're going to have to reference Coulomb's law, okay? And you're going to have to explain. Now, you might not say according to Coulomb's law, but you're going to say, oh, okay, these ions have an overall higher charge, so they're more attracted to each other. Or these ions are smaller than those ions. So when these ions get together, there's not going to be as much of a separation, so the interaction is going to be stronger. All right, so those are the things that you're kind of looking out for, okay? But again, like what we're saying is, if I have a +2 ion that's interacting with a -1 ion, that's going to be a strong attraction, and it's going to be stronger than a +1 ion interacting with a -1 ion. So if I look at the interaction between a magnesium ion and a chloride ion, I know that's going to be stronger than a sodium ion and a chloride ion. And the main reason that is because magnesium's 2+, so a higher charge. So if you go back to Coulomb's law, you'd be plugging in a 2 here versus a 1 here if it was sodium, okay? So I know the interaction between magnesium and chloride is going to be a stronger attraction than sodium and chloride, okay? But that's not the only reason, okay? So, right, we should know that Mg2+ has a smaller radius than sodium 1+. So not only does magnesium have a higher charge, so it's going to interact with the chloride ion more intensely because of the higher charge, it also has a smaller radius. So the separation between magnesium and chloride is going to be less. It's going to be a shorter distance between those two ions than sodium and chloride because magnesium is a little bit smaller than sodium. Okay, so smaller ions, they're going to interact more strongly. Higher charge, they're going to interact more strongly, right? But how do I know magnesium 2+ has a smaller radius than sodium 1+? And this really comes back to Coulomb's law. So we'd have to know that magnesium 2+ and sodium 1+ have the same electron configuration. They have the same electron configuration as neutral neon, right? If we looked at their electron configurations for magnesium and sodium, it would be 1s2, 2s2, 2p6. So they have the same number of electrons, the same number of energy levels around their nuclei, but magnesium has one more proton. And because it has a higher nuclear charge than sodium, but the same number of electrons around it, that greater charge in the nucleus, higher overall charge in the nucleus, pulls those electrons closer to it, and therefore it has a smaller radius. Okay, so for me to know that magnesium 2+ has a smaller radius than sodium 1+, really I have to go back to Coulomb's law, right? So we know the atomic radius trend. Remember, don't get that confused with the ionic radius trend, but the size really depends on how many shells of electrons I have and how many protons are in the nucleus pulling those electrons to it. And it's that balancing act. The more shells, the bigger I get, but the more protons, the smaller I get, okay? But again, that's all based on Coulomb's law, right? That as I gain a proton in the nucleus, my charge in the nucleus increases, my nuclear charge increases. That's going to increase that pull on those electrons, that attraction to those electrons around the nucleus, okay? But then, as I go down, a level on the periodic table, as I go down another, from, row 1 to period 1 to period 2, I gain an energy level. And as I go to period 2 to period 3, I gain another energy level. So the electrons get further spread out because they're in higher energy levels, but then they also start to get pulled closer as you get more protons. And so it's that mix match of Coulombic attraction and Coulombic repulsion with shielding of electrons with other electrons and that kind of thing. So it's those things that you have to look out for, okay? And so having a heavy understanding of Coulomb's law, atomic structure, and that kind of thing is really going to help you explain periodic trends and help you explain strengths of intermolecular forces or ionic bonds or all those things, okay? So if I asked you, what had a higher melting point or which has a greater lattice energy, magnesium chloride or sodium chloride, it's magnesium chloride. And if you had to explain it using Coulomb's law, you'd have to explain, I would explain both reasons. The charge of magnesium is higher than the charge of sodium, so according to Coulomb's law, that's going to increase the attractive force. But also, magnesium smaller than sodium in terms of atoms and ions. A magnesium ion is smaller than a sodium ion, so it's going to get closer to a chloride ion and therefore have a stronger interaction. Okay? All right. So using Coulomb's law to justify, right, you want to explain, higher charge, stronger attraction, and at magnitude, because like a -3 is actually a lower charge, but we're talking about the absolute value of the charge. So a -3 is going to have a stronger interaction than a -2, and a -2 is going to have a stronger interaction than a -1, that kind of thing, okay? And then remember, for Coulombic attraction, it's about being small, increases the strength of the attraction, because the smaller the particles are, the closer they can get to each other, and the closer, like just think magnets, the closer the magnets are to each other, the stronger the interaction between them, right? Two magnets far apart don't really have kind of any interaction, are very weak. You can't even sense it, but as you pull them closer together, boom, they snap together, because the closer they get, the stronger that interaction is, okay? So when are we going to invoke Coulomb's law, or when should we be thinking about Coulomb's law? Anytime we're talking about, strengths of lattice structures for ionic compounds, or, their melting points, or maybe their boiling points, even though, they would have, the ionic compounds tend to have very high melting points, and therefore they would have extremely high boiling points. But it's really just, comparing ionic bond strength, right? Explaining the different trends, the atomic radius trend, the ionization energy trend, the electronegativity trend, the shielding effect. Yes, the structure of the atom kind of explains these different trends, but the structure of the atom kind of shows you, right, what do you got? We know we got neutrons, but we don't really worry about them. We got protons and we got electrons, and electrons are negative and protons are positive, and they're attracted to each other, but they repel. So electrons are attracted to protons, but electrons repel electrons. So it's this balancing act between, you have electron to nucleus to proton attraction, but then you also have electron repulsions within energy levels, and then you have shielding, which the core electrons are shielding the valence electrons from their interaction with the nucleus, because they repel them from the nucleus. And so there's this balancing act, right? So, right, if you have to explain the atomic radius trend, well, we know it increases going down a group, and we know it decreases going across. But why does it increase going down? Because if you go down, you're gaining a lot more protons, right? As we go down group 1, we're going from 1 proton to 11 protons, right? So 1 proton, 3 protons, 11 protons, 19 protons. So we gain a lot more protons in the nucleus. So like potassium has 19 protons in the nucleus, and sodium only has 11 protons in the nucleus. But potassium's bigger, the electrons are more spread out, because potassium has more energy levels, more energy shells, right? Valence shell for potassium is energy level 4. The valence shell for sodium is energy level 3. So the more shells you have, the bigger the radius, okay? But as you go across, left to right, across the periodic table, you don't gain another shell of electrons, but what you do gain is a proton in the nucleus. And so that greater nuclear charge, as you go across, left to right, across the periodic table, pulls the shells that are there closer to it, because that increases the attraction. More attraction pulls the electrons closer, so the radius gets smaller, okay? So we can use, how close things are to their oppositely charged particle, and what's the overall charge of the particles, to explain the strength or the weakness of the attraction, okay? Explaining, PES, binding energy. Binding energy is a lot, pretty much synonymous with ionization energy. But comparing the IMFs, why do we call things that look exactly the light when we draw them? Like if I draw a hydrogen bond between water molecules, that looks very similar to a dipole-dipole interaction between HCl molecules. Why do we give it different names? Well, it's because it has different strengths. But why does it have different strengths? Well, all the IMFs are negative side of a molecule interacting with positive side of another molecule, one particle negative, one particle positive, and their strengths strictly come down to Coulomb's law. So how hard, so a dipole, how negative is the negative dipole? How positive is the positive dipole? The more positive the positive dipole, the stronger the dipole-dipole interaction. The more negative the negative dipole, the stronger the dipole-dipole interaction, right? And then the smaller the molecules, the closer they can get, the stronger the dipole-dipole interaction. So really it just comes down to Coulomb's law, right? So like hydrogen bonding, why are those Fon bonds so important? Well, remember, more polar just means higher magnitude of charge on the dipole, right? More polar means electronegativity difference is bigger. The bigger the electronegativity difference, the more polar it is, and the more polar it is, the higher the charge of the dipoles, and the higher the charge of the dipoles, the stronger they're going to interact in terms of Coulombic attraction with an opposite dipole. Okay, but why is it FO and N? Why is it fluorine, oxygen, and nitrogen bound to hydrogen? Why do those opposite dipoles cause hydrogen bonding and not other ones? And it's two reasons. Those are the most polar, so higher magnitude of charge on the dipoles, but also they're very small. Nitrogen, oxygen, fluorine are very small, so they're going to be able to get closer to the other molecule and thus have a stronger interaction. Okay. So explaining ion-dipole interaction, right? When you dissolve salts in water, the new attractive force that forms is an ion-dipole interaction, right? So the ion, whether it's the positive ion or the negative ion of the salt, interacting with the negative dipole or the positive dipole of the water molecules, right? That's an ion-dipole interaction, okay? And then bond energy diagrams, I'll show you an example of those, but those are the ones that show you the kind of the best distance between two atoms when they're bonded to each other to maximize attraction and minimize repulsion. Because when those bonds form, the attraction you're forming is the electrons of one cloud interacting with the nucleus of the other atom, and so that's the new attraction that's being formed when you form a bond. But as those atoms get closer, their nuclei start to get closer. And if their nuclei get too close, then you have positive versus positive, and it ends up repelling. So you have the sweet spot, the best distance that maximizes the attraction between the two atoms, but it minimizes the repulsion between the two nuclei of the atoms. Okay. So let's just see some practice problems and how Coulombic attraction or Coulomb's law helps us out with answering these questions, right? So most of these are going to be multiple choice questions, but it could be same type of deal in free response. Okay. So again, these are all just from released AP exams. Okay. So here we got different ions and their radii. And we want to know which of these ions is going to have the strongest to weakest interaction with water. So ion-dipole interactions. Okay? Well, the first thing to look at is they all have the same charge. So it's not going to be about magnitude of charge because they all have +2s. Okay? And they're all positive. So they're all going to be interacting with the oxygen side of water because the oxygen side of water has the negative dipole. And so the strongest one is just going to be the smallest one. So zinc's going to have the strongest interaction because it can get closer to the water molecule. And so it's going to have a stronger ion-dipole interaction, and then followed by calcium, and then followed by barium. So we know the answer is zinc is stronger than calcium is stronger than barium in terms of their interaction with a water molecule. So choice A would work, or choice B in terms of choice A and choice B have the right order. But we got to explain why, okay? So because smaller ions have a stronger Coulombic attraction in water, that sounds good. Because smaller ions are more electronegative, no. Okay, smaller ions are not more electronegative. Okay, so so B has the correct order, but it doesn't have the right explanation. A is the correct order with the correct explanation in Coulombic attraction. Okay. So again, for this one, choice A is correct. Okay. So for this next one, I just kind of want to, it's really not. Well, it kind of is Coulomb's law, right? When you separate things that are attracted to each other, that requires energy, okay? And when things are attracted to each other come together, that releases energy, right? Axing is taxing and forming is warming, right? Endothermic is axing, requires energy. Forming is exothermic. Forming is warming, it releases energy, okay? So this is showing basically a salt, and you could call this water. I don't think they say water, they say a polar solvent. So what's an example of a polar solvent? Water. So you could say each of these spheres represents a water molecule, and you got a negative ion and a positive ion. Now, maybe the smaller sphere is the negative, the positive ion, and the bigger sphere is negative, but it could be the opposite way. So we have positive and negative ions, and we got polar molecules that have dipoles, right? Opposite dipoles. So when a salt dissolves in a polar solvent like water, right, the ions have to separate, so you have to break the ionic bonds. So step one here is endothermic. It requires energy to separate those ions that are attracted to each other, right? Coulomb's law, to separate magnets requires energy, right? The water molecules, or the polar solvent molecules in this case, have to spread out a little bit more to make room, so they have to break their IMFs. If it was water, you got to break some hydrogen bonding between water molecules to make these holes fit for the ions that are going to fill them in, right? So that separating water molecules, separating polar molecules that are interacting with each other, that requires energy. So step two is endothermic. But when those ions fit into the holes, you get new forces of attraction form, ion-dipole interactions, and that releases energy because those attractive forces are being formed, not being broken, right? So step one and step two are endothermic, and step three, that final step, would be exothermic. So the answer is choice D, okay? But just separating things that are stuck together, that requires energy, endothermic, and when new things stick together and turn on those interactions, like ion-dipole interactions, or hydrogen bonding between water molecules as water condenses, that releases energy, right? Forming is warming, okay? All right, so in this one, we got a PES, but notice they just give us the 1s peak for both nitrogen and oxygen. And so the main thing here is noticing that the 1s electrons for nitrogen have a lower binding energy than oxygen. And so what binds the electrons to the atom? Their attraction to the nucleus. So this is saying that oxygen's 1s electrons are more attracted to the nucleus than nitrogen's 1s electrons, okay? And the only reason is because oxygen has one more proton, okay? So the answer here is D. Nitrogen atoms have a smaller nuclear charge. To say you have less protons in the nucleus means your nuclear charge would be less, right? If I have 7 protons, I'm +7. That's my nuclear charge. If I have 8 protons, my nuclear charge is +8. So oxygen has a +8 nucleus. Nitrogen has a +7. Where do those numbers come from? That's their atomic number. That's the number they have in their protons they have in their nucleus. So you could, oxygen has a higher nuclear charge, which creates higher binding energy, or nitrogen has a lower nuclear charge, which creates weaker binding energy. Now, what a lot of students do for this one is they answer B, because when they see an oxygen and nitrogen PES question, a lot of times they're looking for the exception to the ionization energy trend. And if you recall, there's a couple of exceptions to ionization. As you go left or right across the periodic table, ionization energy increases, but there's a couple of blips, especially as you go across period 2 and period 3 on the periodic table. As you're going across period 2, you get an exception between beryllium and boron, and then nitrogen to oxygen. And as you go across period 3, it's magnesium aluminum. There's an exception to the trend. It actually gets easier to remove an electron from aluminum than it is magnesium, even though aluminum's further to the right. And the same thing happens between sulfur and phosphorus and sulfur. And so a lot of people are primed for that, and they're looking for that. And if this question had asked why does oxygen have a lower first ionization energy than nitrogen, the answer is B. Remember, like in oxygen's 2p sublevel, it goes up, 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 down, whereas the orbital filling diagram for nitrogen is just up, up, up. So because oxygen has a pair, electrons paired up in its p sublevel, that adds electron-electron repulsions, which weakens the attractive force of the electron to the nucleus, so it's actually easier to remove. But that's not what this question is asking. So you gotta be aware of that. But that same question shows up here. Okay, so this was a different year, a different test. But here, notice they have the atomic radius trend for boron to neon, and it just gets smaller, and that makes sense. But notice nitrogen to oxygen, first ionization energy actually goes down. It's actually a little bit easier to remove oxygen's first electron than nitrogen's first electron. And by first electron, I mean the furthest one away from the nucleus, the one that would be easiest to remove, right? And it's because of the extra electron-electron repulsions in oxygen. So let's find that one. There's your repulsion between paired electrons in oxygen's 2p orbitals. Yes, that one. Right? Nitrogen doesn't have that because nitrogen has 3 electrons in its 2p orbital, and remember, in a 2p sublevel or 2p sublevel, and in a 2p sublevel, there's only 3 orbitals. So each orbital has 1 electron, but in oxygen it has 4 electrons, but only 3 orbitals. So 2 of those electrons are paired up, and electrons don't like to be paired if they don't have to be paired, right? Okay. So here we got sodium fluoride's boiling point, magnesium oxide's boiling point. Remember, these are ionic compounds, so it depends. The strength, the amount of energy required to vaporize these things or to melt these things is strictly comes down to Coulomb's law. And it's asking us, what would we expect sodium chloride's boiling point to be? Is it going to be less than sodium fluoride, or is it going to be greater than both of these, and it's going to be greater than magnesium oxide, or is it going to be somewhere in between? And we shouldn't have to look at the periodic table for this. We should know that, well, I mean, we could, at a quick glance. Chloride has a bigger radius than fluoride, but in case we didn't know that, it's here. So that means we should expect sodium chloride to have a weaker interaction than sodium fluoride. So we should expect sodium chloride's boiling point to be less than this number, because the Coulombic attraction between sodium and chloride is not going to be as strong as sodium and fluoride, because sodium and fluoride are going to have a shorter distance between them because fluoride's smaller than chloride. Okay, and that's it. Okay, so it says sodium chloride will have a lower boiling point than sodium fluoride because the Coulombic attractions are weaker in sodium chloride than sodium fluoride. Yes. Okay. Let's see if there's another one. No, it says, so that's the only correct, that's the only answer choice that's saying sodium chloride would be lower than sodium fluoride. So obviously that has to be the right explanation. Maybe they could trick you and say and use the word atomic radius instead of ionic radius, and we want to make sure we're dealing with ions, so we would say ionic radius and not atomic radius, but they don't get that tricky all the time on the AP exam, okay? So here, it's just kind of knowing the trends. We don't really need to know why the trend is what it is, but calcium and potassium are in the same row, but potassium is the furthest one to the left, right? It's in group 1. So we should expect potassium to have a greater radius than calcium. So we know that, it's not choice D. We know that it's either got to be A or B, right? It has to have a greater radius than calcium. So we know C and D are out. And it would have a lower first ionization, because the further the electrons are away from the nucleus, the easier they are to remove. So we know it can't be choice B. So it has to be choice A, right? So choice A, choice A is the correct one there. Don't know why I had choice D, okay? But again, why? Okay, why does potassium have a bigger radius? Well, because it has 1 less proton. So its nuclear charge isn't as high as calcium. So the electrons it does have, and it has 4 energy levels of electrons, but so does calcium. They're in the same period of the periodic table, so they have the same number of energy levels. But because potassium has 1 less proton, those electrons are going to be a little bit more spread out than calcium's electrons, and therefore have a bigger radius. And because that valence electron in potassium is a little bit further away from the nucleus, it's a little bit easier to remove, so it'll have a lower first ionization energy. And sorry, I said A. The correct answer is B, okay? Higher radius, lower first ionization energy. Sorry, okay, the answer is B here, okay. All right, so here, remember, dashed lines means an intermolecular force, and a solid line means a bond, a covalent bond. So here we have a single covalent bond, and here we have a hydrogen bond, right? A dipole-dipole interaction between hydrogen fluoride molecules. But remember, we wouldn't call that a dipole-dipole interaction. We would call that a hydrogen bond. It's a special type of dipole-dipole. But basically, it's asking, what is this diagram showing us? It's showing us that a covalent bond is going to be stronger than an IMF. And the main reason is because the IMF, within a molecule, the atoms are closer to each other, right? And so PM means picometers here. So the bond length is shorter than the molecule to molecule length. And because they're closer to each other here, they're going to have a stronger interaction, okay? So which of the following best accounts for the two different distances? The answer is B here, the difference in strength between covalent bonds and intermolecular forces. So this is just trying to bring in Coulomb's law and tell you, why there's a difference in strength between these atoms. When it's these two atoms here versus these two atoms here, they're the same atoms, but these are atoms within a molecule. These are atoms between different molecules, and the reason the difference is in strength comes down to the distance, because they would have the same dipoles, right? They would have the same magnitude of dipoles, but why would this interaction be stronger? Also, because this interaction, they're closer to each other here than they are here. So the closer they are, the stronger the interaction. All right. So let's keep on rolling. Okay. So this is just asking, identifies which of the following correctly identifies which of them have a higher first ionization energy and why. Okay, so just based on trend, we should know that argon is further to the right than chlorine when we look at a periodic table. So argon has the higher first ionization energy. So we know A and B are incorrect. Argon has it. Now, a lot of kids will think back in chemistry 1 where we're always talking about we want the same electron configuration as a noble gas because a full valence shell is more stable, and that's the whole octet rule. Elements gain, lose, or share electrons to get to 8. And so a lot of kids are going to want to say, because argon has a completely filled valence shell. And yeah, argon's stable, argon's electron configuration is more stable than chlorine's because it has a full valence shell of electrons. But that's not why it's harder to remove an electron from argon. It's harder to remove an electron from argon because argon's valence electrons are more attracted to its nucleus than chlorine's valence electrons. And the reason that is because argon has one more proton in the nucleus. It has a greater nuclear charge. Now, if they say the effective nuclear charge, the way you can calculate that is protons minus core electrons. So chlorine and argon both have the same number of core electrons. Their valence electrons are in energy level 3, so their core electrons are the energy level 1, energy level 2 electrons. So they both have 10 core electrons. But since chlorine only has 17 protons, if you do 17 minus 10, that's a plus 7 effective nuclear charge. But if you do 18, argon has 18 protons minus 10, that's a plus 8 effective nuclear charge. And the higher the effective nuclear charge, the more attracted the electrons are, the harder they are to remove. But really, they could just say it has a greater nuclear charge. They didn't have to use the term effective nuclear charge here, okay? So here is just kind of, just a review, right? If this is a water molecule, remember the H's are the two smaller spheres here, right? So if this is Mickey Mouse, the ears of Mickey Mouse are the hydrogens, and those are the positive dipoles. And the bigger circle here, that's the oxygen, that's the negative dipole. And we got to just remember opposites attract. So we got to know that silver is a positive ion and nitrate's a negative ion. So if water is going to interact with silver, it's going to be the oxygen side facing silver. And if water's interacting with nitrate, it's going to be the H plus side, the hydrogen side facing the nitrate, because opposites attract each other. Okay? And if we want to show this dissolved in water, first we have to remember the ions have to be separated so we can eliminate choice D, because if they were together like this, that would be representing silver nitrate solid, okay, like undissolved. So they have to be separated like in A or B or C, but what's going to be the correct orientation? C looks good for the silver because you have oxygen facing the silver, but you also have oxygen facing the nitrate. That's wrong, okay? Here we have the positive side of water facing the positive ion. That's wrong. and we have the negative side of water facing the negative ion, that's wrong. So it's got to be A, but let's look. Oxygen's facing the positive ion, and hydrogen's facing the negative ion. So choice A is correct here. And again, it's just remembering opposites attract, like charges repel. So kind of Coulomb's law, but not using Coulomb's law to justify it. Okay, so these are those bond energy diagrams I was talking about, right? So diagrams that look like this. So remember how to interpret it, right? It has a negative energy because remember, this is showing the amount of energy released when a bond is formed, and forming attractive forces like a bond is warming, right? So it releases energy. So as the two atoms get closer to each other, right, it increases the attraction. And what are you increasing, right? The electrons in this cloud are attracted to that nucleus, and the electrons in this cloud are attracted to that nucleus, right? And so as they get closer, that attraction builds, but eventually you get to a point where you keep forcing them closer together, and then they start to repel each other because the nuclei, which are both positively charged, start to repel each other, right? And so the bottom of this well here, that's the sweet spot, right? That's maximizing the attraction and minimizing the repulsion between the nuclei. And right here, that's going to be my bond energy. And it's negative again because that's how much energy is required or released when the bond forms. And notice it's energy per mole of bond. It's not just one bond has that much energy. It's a mole of those bonds, right? But if you made this a positive, that would be the amount of energy required to break a mole of those bonds. So, right? But then if you go up to this axis, this is measuring the distance between the nuclei. And so if you go to the bottom of the well, that's the bond energy for that bond, and this is the bond length for that bond, and it's usually measured in picometers, right? So if we go back up to this question, it gives us 3 different bonds to consider. Well, whatever this bond is, it's the shortest bond, right? Whatever this bond is, it's the longer of the 3 bonds. But whatever this bond is, it's the stronger of the 3 bonds, because, wow, look at that bond energy compared to these. Okay, and it's saying X2, Y2, and Z2, so they're diatomic elements. And this is one of those reminders, hey, remember, nitrogen has a triple bond, so it's very strong. So obviously Y2 is nitrogen. Oxygen has a double bond, and hydrogen has a single bond, and all the other halogens that are diatomic have single bonds. But hydrogen is going to be the shortest of those bonds because hydrogen is so small. So I know Y2 is nitrogen because it's the strongest bond. I know X2 would be hydrogen because it's the shortest bond, and that would leave this to be oxygen. So it would go X2 is hydrogen, Y2 is nitrogen, Z2 is oxygen. So choice A is the correct answer, choice here. Okay. All right, so here we got PES again. But notice it's just a 1s peak, so it's not a complete PES diagram where I can identify the element. And they're asking us which one is which. So it's carbon versus fluorine. And I just right off the bat, fluorine has to be X and carbon has to be Y. And it's because fluorine has more protons. So greater nuclear charge, greater effective nuclear charge, if you wanted to say that. But it has nothing to do, so it's not ionization energy. So peak X is fluorine. Because fluorine has greater nuclear charge than carbon. There we go. Choice B. Okay. Here we got ions in the radius. And we want to know which one's going to have the weakest interaction. Okay. So a lot of students get this wrong because they go to the bigger the radius is going to be a weaker interaction. So they choose calcium. But you got to be careful because calcium and sodium are pretty similar in size. That's not a big difference. But calcium has a 2+ and sodium only has a 1+. So it ends up being sodium has the weakest interaction because it's one of the bigger ones and it has the lower charge between calcium and sodium. So a lot of students would go with the biggest radius here, but it's not just about the smaller radius being stronger. It's also about the overall charge. So this has a very similar radius to sodium, but it is a +2. So that's going to be a stronger interaction than just the +1 of sodium. So the answer, the one that has the weakest would be sodium. The one that would have to be the strongest, it would be hard to tell because there is a pretty big difference between 60 and 80, 81. Now, IN has a 3+ charge here, so that's probably going to be the answer, but lithium can get really close to a water molecule, so that might be stronger. They wouldn't put you in that situation without giving you more information to figure out which one's which. But in this case, the weakest one would be sodium. Okay. So here's kind of like just an IMF question. So I should be able to look at this and know it's polar with dipole-dipole interactions. This is polar with hydrogen bonding, and this is non-polar with just London dispersion forces. Now, why is a hydrogen bond stronger? Well, it's because this bond, right? This bond is more polar than the carbon-oxygen bond is polar, but not as polar as oxygen-hydrogen. So the negative dipole on the oxygen is going to be higher than that negative dipole. The positive dipole on this hydrogen is going to be stronger, higher in charge than the dipole of carbon here, the positive dipole of carbon here. So the dipole-dipole interactions in this aren't going to be as strong as the dipole-dipole interactions in this. And remember, the interactions between these molecules, we would actually call hydrogen bonding. We wouldn't really refer to them as dipole-dipole interactions. And then this one doesn't have any polar bonds, and so it just has London dispersion forces. So increasing boiling point, we would know 1-propanol would be the biggest, highest boiling point, followed by acetone, and then butane would be the weakest. So the correct answer choice is B here. Okay. But again, using Coulomb's law to kind of explain why, why is that bond more polar than that bond? Why are these dipole-dipole interactions more intense than those dipole-dipole interactions? And again, it's Coulomb's law. Okay. So here we have successive ionizations, ionization energy 1, 2, and 3. So, remember, whenever you're given this, you're looking for the big jump. So obviously, whatever X is, it has 2 valence electrons, and this third electron is being removed from the next energy level down. So why is there such a big jump? Well, this electron is much closer to the nucleus than these electrons, and that's why it's a lot more difficult to remove. And the reason that is because these must be, like, let's say this was magnesium. So magnesium has 2 valence electrons, so this would be, the energy to remove those 2 valence electrons, but its next electron being removed would be energy level 2. And if it's in energy level 2, it's a lot closer to the nucleus, and then it's going to be a lot more difficult to remove. Okay. Which of the following is most likely explanation for the large difference between the second and third? So the electron removed during the third ionization is a lot closer to the nucleus because it's in a lower energy level. So choice C here. Okay. Here again, successive ionizations. The big jump is between 3 and 4. So electron 1, 2, and 3, those are valence electrons. This would be a core electron or the electron on the next energy level down. So whatever element X is, it has 3 valence electrons. So it's in like aluminum's group, boron's group. So if it were to react with oxygen, think aluminum is a 3+ ion, oxide's a 2- ion, crisscross, so it would be Al2O3, so choice C. But even if it was boron, it would be B2O3. Okay, so this would be the correct answer choice here. But it's because I knew that since this ionization energy was so much stronger than this one, that these represent valence electrons and these are representing core electrons. Okay. So here we got a free response question. Notice they give you ionization energy. Now here, look at this. It says energy per mole of electrons being removed. So if you wanted to find the energy of just one electron, to remove just one electron from one sodium atom, you would have to divide this by Avogadro's number, or you would divide this by Avogadro's number to figure out potassium. But why does sodium have a higher first ionization than sodium? Well, we know that ionization energy decreases as you go down, but why? Because the electrons get further away from the nucleus. Why? Because sodium has 3 energy levels and potassium has 4. So because potassium has 4 energy levels, it has a bigger radius than sodium. And because that electron is further away from the nucleus, it's easier to remove. Even though potassium has more protons, it's further away, so it's easier to remove. And that's why potassium has a lower first ionization energy than sodium. So based on principles of atomic structure, explain why the first ionization energy of K is lower. So that's what I'm talking about, using atomic structure, but tying it into Coulomb's law. Why potassium having a bigger radius, why does that make it easier to remove? Well, what's holding the electrons onto the nucleus or onto the atom? their attraction to the nucleus. Well, that attraction weakens the further away from the nucleus they are, right? As distance or separation increases, Coulombic attraction decreases. So it's easier to remove an electron that's further away from a nucleus than one that's closer, okay? So that's what's going on in part B, okay? And then here, again, knowing that, knowing our periodic trends, knowing Coulomb's law, knowing that in this, lithium would be the smaller ion because a lithium plus ion is smaller than a chloride minus ion. So like being able to know that this is the positive ion and this is the negative ion, knowing that this is the oxygen, so that's the negative dipole of water. So if you drew water molecules surrounding these ions, the oxygen side of water would face the positive lithium ion, which is the smaller sphere, and the hydrogen side of water would face this bigger sphere, okay? So notice this one just says draw one formula unit of this dissolved, so you'd have to draw one chloride and one lithium, but they would have to be separated, so you'd have a big sphere here, small sphere over here, and then you would draw a couple water molecules, but drawing them around in the correct orientation. So again, it would be a picture that kind of looks, you would want to draw something that looks like this, right? Where the smaller one was the lithium ion and the bigger one was the chloride ion, and then chloride is negative, just like nitrate, so water would face it like this, and silver would face it like that, okay? But again, I think Coulomb's law is going to be even a bigger part of the AP exam this year. Maybe not for round 2. I know we're taking the second exam this year, not the first exam. But I'll be curious to see that May 6th exam, especially on the free response, do we need to reference this law a little bit more than usual because they're giving it to us on the formula sheet. All right. Anyway, just something to look forward to. All right. So hopefully that helps you with your review and you found it informative. Have a great day.